So in first year chemistry, you guys learned how to draw the Lewis structures for molecular compounds. And we're going to be expanding on that today, looking at molecular geometries and electron domain geometries. But the first thing that I wanted us to go over was actually how covalent bonds form. We know it's the sharing of electrons, but specifically how we can determine the energy that's involved in that bond, or the bond strength. So if you look at this graph, you have on the y-axis energy, which is actually potential energy, and then on the x-axis is the distance between two hydrogen atoms. So if you are far to the left on this graph, that means that the atoms are extremely close together, while if you're on the right-hand side, then the atoms are going to be far apart. So if you are to the far right of this graph, if you notice, the potential energy actually almost reaches zero, and that's because there's no attractive or repulsive force between those atoms. They don't actually interact with one another. Now, as those atoms get closer and closer together, as you move across and to the left on this graph, you'll see that the potential energy is decreasing. And as the distance between these atoms decreases, the strength of the bond actually increases, and that can actually be seen in the negative value for the potential energy. So the more negative the potential energy, the stronger the bond is. Once you've passed that point, that low point, the point at 0.74 angstroms, if you notice, the potential energy starts to increase. And it starts to increase, meaning that the strength of the bond between those two atoms, that covalent bond between those two atoms, gets weaker because as they get closer and closer, the nuclei of those atoms actually start to repel one another. And so if you're given this graph and you're asked what is the bond strength, all you need to do is look for where the potential energy is the most negative or the smallest, and that will be the bond strength between two atoms that have covalent bonds. So what happens if, when we're drawing our Lewis structure, what if the number of valence electrons we're allowed to use don't fulfill the octet rule? Well, that's when we get into resonance structures. So I'm going to provide you with an example in order to explain what resonance structures are. So if I have ozone, O3, then the total number of electrons that it would have would be 18 valence electrons. Now to draw this using the octet rule, I would have my 3 oxygens, and then each oxygen needs 8 valence electrons. So I'm going to have 2 pairs on that central oxygen to make a total of 8, and then 6 on the oxygen on the left-hand side and 6 on that. Now, if you count the number of valence electrons that you use, that's actually 20 valence electrons, not 18. And so as a result, you're going to need a double bond. And so the question becomes, well, where do I put the double bonds? And the answer to that is when we're drawing the resonance structure, we're going to draw 2 different versions of ozone. So the first one, we're going to put the double bonds on the left-hand side. So I'm going to draw my oxygens, and I'm going to put the double bonds on the left-hand side, and then I'm going to complete the octet. So I'm going to put 2 pairs on that oxygen, 3 pairs on that oxygen to make a total of 8, and then 1 lone pair of electrons on the central oxygen. The other form of ozone that could exist, you could have the double bond on the right-hand side, and so I need to draw that. So I'm going to show a double arrow to represent the fact that this is resonance, and I'm going to draw the double bond on the right-hand side. So a single bond on the left, double bond on the right, 3 pairs of electrons on that oxygen, 2 on that, and then 1 lone pair of electrons on the central atom. Now the important thing for you to know is that for resonance structures, it's not that you have 2 different forms of that ozone. Instead, ozone exists as a mixture of those 2 forms of ozone. And so the best way to explain that, the fact that you don't just have one or the other and instead a mixture, think about blue and yellow. If I took blue, imagine the ozone on the left-hand side were blue, the ozone on the right-hand side were yellow. If I mix them together, I would have the color green. And so that's resonance. We draw it the way that it's drawn right there simply because that's the easiest way of representing resonance. But in fact, those 2 do not actually exist. Instead, it's a mixture. So if we're talking about bond length, the length of those bonds, it's not that you have a double bond and a single bond, and instead it's an average of the two. So what's the average of a double bond and a single bond? Well, it's a 1.5 bond. And so each of those bonds is actually just 1.5, the bond between each of the oxygens, and that's resonance. Now I'm going to take the Vesper model, I'm going to really quickly explain it, and then I'm going to expand upon what we've already talked about regarding Lewis structures in order to determine the shape that those molecules take. Now the Vesper model, what it states is that molecules will form in such a fashion that they minimize the repulsions amongst them. So the atoms themselves are going to be spaced in such a way to minimize their repulsions of one another. And so how exactly does that affect the shape of the molecules that we created when we created our Lewis dot structures? Well, there are a couple of terms we need to go over first. There is the electron domain geometry, and the electron domain geometry includes the bonding pair, and the bonding pair is just the pair of electrons that are shared by the atoms. That's represented just by a line, by the sharing of electrons. And then there's the non-bonding pair, which is the pair of electrons that are found just on one atom, the dots that you see, the electrons that are not shared. So when we're counting the number of electron domains that a molecule has, each non-bonding pair, each single bond and each multiple bond, those represent just one single electron domain. So if you look at this example of ozone, notice on that central oxygen in the center, you've got a pair of non-bonding electrons, you've got a double bond, and you've got a single bond. And so since each of those represents one single electron domain, the electron domain, the number of electron domains you have there is 3. Now we're going to take that number of electron domains and we can use that to determine the electron domain geometry. And so the electron domain geometry simply relies on the number of electron domains. And so we'll look at examples in just one second. Now, that's the electron domain. The molecular geometry, that is actually the arrangement of the atoms in a molecule, not the geometry based on the number of electron domains. So let's look at some examples. So when we're determining the electron domain geometry and the molecular geometry, keep in mind that if you have no non-bonding domains, then your electron domain geometry and your molecular geometry are going to be the same. So let's look at all of these examples. If you have 2 electron domains, the shape is automatically going to be linear. Now, in this example of CO2, notice you have 2 bonding domains and no non-bonding domains. Therefore, the molecular geometry is also going to be linear. And with regards to the bond angle, the bond angle here is going to be 180 degrees because it's flat. Now, if you have 3 electron domains, let's say, for example, you have 3 bonding domains and 0 non-bonding domains, like in the case of BF3. Now, in this case, the molecular geometry is going to be the same as the electron domain geometry. And for bond angle, notice that you have 3 different angles that would make up a circle. Therefore, each of those angles is going to be 120 degrees. Now, if instead of 3 bonding and no non-bonding, what if I had 2 bonding and 1 non-bonding? Well, in that case, the molecular geometry is going to be different from the electron domain geometry. The electron domain geometry is still trigonal planar because it has 3 electron domains, but now the molecular geometry is different. The molecular geometry is bent. And I'm going to be talking about how non-bonding domains affect the angle, but just for you to know, it actually makes that angle smaller. So while we might anticipate that the bond angle for that bent shape would be 120 degrees, just like for trigonal planar, it's actually a little bit less. It's about 119. But notice you don't need to memorize those numbers, just the ones that are in gray. If I have 4 electron domains, 4 bonding and no non-bonding, again, my molecular geometry and my electron geometry are going to be the same, and it's going to be tetrahedral. Now, if instead I have 3 bonding domains and 1 non-bonding domain, like in NH3, notice it's 3 bonding because you have 3 hydrogens, and then 1 non-bonding because you have 1 lone pair of electrons there, then the molecular geometry is going to be trigonal pyramidal. Notice that the electron domain geometry is now different from the molecular geometry. And really quickly, for tetrahedral, the bond angle, instead of being 120, is actually going to be 109.5. And all of these bond angles, remember, result from your Vesper model, the fact that these atoms are trying to avoid one another as much as possible. So as we would predict, the bond angle for trigonal pyramidal should be less than that, and it's actually 107.3. And I'll talk about why in just one second. The last one, if instead of having 3 bonding and 1 non-bonding, what if I had 2 bonding domains and 2 non-bonding domains? Well, in that case, the electron domain geometry is still going to be tetrahedral, but the molecular geometry is going to be bent. And the angle is going to be even less than it was when you only had 1 non-bonding domain. Okay? Now the question arises, well, what if you have more than 8 electrons around your central atom? Can you have more than 8 electrons around your central atom? And the answer to that is yes, as long as you're in the 3rd energy level. And the reason why is as soon as you reach that 3rd energy level, those atoms have access to the d orbital. And the d orbital allows them to hold more than just 8 electrons. And so the next question should be, okay, but then what happens with shape? And so I'm going to be introducing 2 new electron domain geometries, and therefore 7 different molecular geometries that you haven't been introduced to yet. But it's all very manageable, and you'll get plenty of practice with it in class. So if instead of 4 electron domains, if you have 5 electron domains, if you have 5 bonding and 0 non-bonding, then the electron domain geometry and the molecular geometry are going to be the same, and they're going to be trigonal bipyramidal. If you look at that shape, you can see that you have a trigonal planar shape in the middle, and then you have a linear going from top to bottom. And so the bond angles for a trigonal bipyramidal is going to be 180 because you see that long line. It's going to be 120 because you got that trigonal planar shape in the middle. And then you're also going to have 90-degree angles because if you notice the one on top and it makes the L, that would be 90 degrees. And so you've got 3 different possible bond angles for trigonal bipyramidal based on the Vesper model. Now, if you still have 5 electron domains, but instead you have 4 bonding domains and 1 non-bonding domain, which you can see in SF4, then the molecular geometry is going to be called seesaw. You can kind of imagine that as a seesaw with the legs going up and down. If you have 3 bonding domains, but only 2 non-bonding domains, then it's going to be T-shape. And then if you have 2 bonding domains and 3 non-bonding, then it's going to become linear again. Now, I'm not going to expect you to remember all of these angles, so you're good. I'm not going to give those to you. But notice that all of these have the same electron domain geometry, even though they have different molecular geometries. And then finally, if instead of 5 electron domains, you have 6 electron domains, then the electron domain geometry is going to be octahedral. And octahedral has 2 different bond angles. One of them is 90 degrees, which you can see. And then the other one is going to be 180 degrees. Now the 180, you can see from that straight, all of those make straight lines. And then they're ones that are perpendicularly oriented with one another. So if you have 6 bonding domains and no non-bonding domains, the molecular geometry is octahedral. If you have 5 bonding domains and only 1 non-bonding domain, then it's going to be square pyramidal because it makes a square on the bottom. And then finally, if you have 4 bonding domains and 2 non-bonding domains, then it's going to be square planar. So all of this talk about bond angle, the ones that were given to you in gray, you are expected to know. However, if you have non-bonding electrons or multiple bonds, that's going to affect the bond angle. And you don't need to memorize them, you just need to know how that affects the bond angle. So the first question is, how do non-bonding electrons affect the bond angle? Well, as the number of non-bonding electron pairs increases, that's going to cause the bond angle to decrease, as I mentioned in the previous slides. This is because the non-bonding electrons, they take up more space, and they take up more space because they're only going to be attracted to the nucleus of one atom, while instead bonding electrons are attracted to the nuclei of the 2 atoms that are sharing them. And so non-bonding electrons take up more space, and as a result, they're going to repel any adjacent domains or any adjacent atoms more than bonding electrons would. And so as you can see here, for CH4, that is the bond angle for a tetrahedral. Now if you add one pair of non-bonding electrons, like an NH3, notice that that reduces the bond angle. And if you have two pairs of non-bonding electrons, that reduces the bond angle even more. The last thing you can do to bond angle is you can have multiple bonds. Well, a double bond or a triple bond, they actually exert greater repulsive forces than single bonds do, and that's because they have a higher density of electrons. They're sharing more electrons between them. And therefore, they're going to act kind of like non-bonding electrons where they are repelling adjacent atoms. So as you can see here, you would expect, without that double bond, you would expect the bond angle between all of those to be 120 degrees. But since there's a double bond between carbon and oxygen, that double bond repels the chlorine atoms downwards, reducing the bond angle between the chlorine atoms and increasing the bond angle between the chlorine and the oxygens. So while you can memorize the traditional bond angles when you're not dealing with non-bonding electrons or double or triple bonds, as soon as you add non-bonding electrons or double or triple bonds, the bond angle will change, and you simply need to know if it's going to increase or decrease the bond angle.